to talk about data-driven methods for characterizing functionality and control neural networks.
Okay. Thanks all for coming. This is a fantastic group. I'm really excited to be talking to some more of you later. I'd especially like to thank the organizers. You guys did a great job. I feel like we're being very well taken care of, which math conferences, they just, here it's nice, very fancy. I hope everybody feels it's fancy. So I'm gonna talk about data and particularly a dynamical systems viewpoint of data and what we can do with data. And I want to start building models directly from data. Try to take as many priors away that you have from what you think the model is and try to use the data itself to inform that. Now, mathematically, it's very simple. This. Now, AX equal to B is a little deceiving. We all think we know how to solve this. I thought I did. I'm a professional, supposedly, mathematician. I've been teaching in the applied math department for a lot of years. But it turns out we're not just going to backslash this on MATLAB. Okay, we've got to think a little bit more about what we're trying to actually get out of AX equal to B, partly because nowadays in our big data formats, matrices aren't square. They tend to be massively over or under determined. So when you start thinking about this kind of AX equal to B, you're starting to have to make choices. And those choices involve what are you going to do about the fact that when it's underdetermined, right, or over, you're going to have to make some choices about what do I actually want out of this thing. Okay? So that's kind of what we're going to go after here. Now this slide deck is slightly different than the one I had on there because I made some modifications. So I'm going to wing it here and see how I go. So let's talk about AX equal to B. I have my little example left over here. Look, I have some MATLAB code, and I'm going to just solve it. So I make myself a random matrix A, and what I have there is 100 rows by 500 columns, right? So I have 500 unknowns, 100 constraints. So I have an infinite number of solutions that can potentially come out of this. Which one do you want? What does MATLAB give you? Because I can just go through and I can solve it with things like this, backslash, pseudo-inverse. There's a bunch of others. Do you know how many there are in MATLAB that solve this AX equal to B? It's quite a few. I think there's at least 7 or 8 at your fingertips. So which one do I want? Which one might you like? I'm going to tell you some of the differences. So some of the differences here look at things like, well, I might want to take a solution, and a lot of times what happens is when you write down these solutions, you might say, I want the solution just as the smallest L2 norm. That's almost a standard thing to expect out of this. And if you do that, what ends up happening is these 500 unknowns to get the smallest L2 norm, all 500 variables become important and small. And so if you look at a histogram of the distribution of values, that's this bottom row here. So it gives me lots of very small values, no zeros. However, what we are starting to look at now, especially has become important, is looking at sparsely promoting solutions. And so now this is going towards L1 norms instead of L2 norms. Why don't you give me the solution, the smallest L1 norm? What this does is tries to set as many of those terms to 0 as possible. And that is the top solution, right there. 400 zeros, 100 that are not 0. By the way, the backslash, at least for this system here, gives me, in fact, the same kind of thing. It gives me a different sparsity pattern. And the backslash, at least in this case, does a QR decomposition. And if you do underdetermined system, it actually does L2. The pseudo-inverse does L2. So these are different strategies for solving just AX equal to B. And so I'm going to propose that what we want to do is start thinking about sparsity promoting techniques for this AX equal to B. The other connection I want to make is to model selection, because I'm going to take data and build models. Well, model selection's been around for a long time. 1950s, you have this idea of KL divergence to evaluate a model, which is you take your model that you made up, you look at it statistically over lots of runs, lots of realizations. You look at your data, and you look at its statistics, and you compare these. And you can compute this KL divergence. Later in the 70s, you have the Akaike information criteria. So AIC says, well, actually, you're not going to give me one model. You're going to give me a suite of models, 6, 10. You're going to evaluate them all statistically, and relatively speaking, ask which one is the closest to the statistics of your data. Now, this was generalized to 78 BIC, which is a different information criteria, very closely related. But the nice thing about BIC, it has a theoretical guarantee that if in 1 year, if you have enough data and the correct model is actually one of the models there, it's guaranteed to converge to that model. That is not the case for AIC. You could have the right model, and in some cases, you won't converge to it. So we want to still use AIC and BIC to evaluate how we do this model selection. And it's going to be very important for the concept of taking care of overfitting issues. I'm giving you here a little graph of error versus the number of terms or complexity of your model. If you give me 1 million data points, I can give you a model that will give you 0 error. I just need 1 million different terms in my model, which of course is totally wrong because you've completely overfit it to the data. So what this is trying to say to you is that if you use information criteria, if you don't have enough terms, you get very high error, and eventually it drops down. And over there is overfitting. And then if you do cross-validation, you get some region here where that gets lifted up, and you have this region here, the Pareto front, where you want to look at the most likely candidate models that are available to you. Okay, here's the complication for all of us, I think. This is why we have jobs and conferences like this, is because nonlinearity is sitting in all of our systems. We may or may not know its forms. We may know part of it or not. But I think nonlinearity is driving a lot of the interesting dynamics we want to look at. And even in these large systems, not only does the nonlinearity drive interesting dynamics, but often it drives it into low-dimensional structures that dominate the dynamics. And to get a view at these low-dimensional structures, you can do things like the SVD, PCA, POD, whatever community you come from has different names. Dynamic mode decomposition is another one that's been recently advocated. Tensors, there's a bunch of different ways to get down to low-rank subspaces. Then there's the idea of what should I be observing in the first place? Just because you measured a voltage doesn't mean that's the right variable for your system. Right? So I think oftentimes what we think about is whatever I measured, I'm the expert. I wrote down the right variable. Maybe it's the wrong variable. Okay? It could be not wrong because it's the wrong thing to measure. It could be wrong just simply from the point of view of, think about Berger's equation, which is a nonlinear PDE with this wave-breaking phenomena and a diffusive regularization. And you could write it in those variables. Or I could tell you about the Kohl-Hopf transform that turns it into a linear diffusion equation, which I can solve exactly. I would say the right variable is to put it into the heat equation, not keep it in the nonlinear wave equation. Okay, here's our goals. In our data, we would like some diagnostic tools. Hopefully, we can keep some interpretability. And I think this is a real challenge when you start to get to deep neural nets these days and some of these machine learning methods, which are fantastic at often getting good predictions with very little interpretability. Okay? And I think I side more on the fact that I would really like interpretability. I would like to use this to get future state predictions, and of course that's heading towards control, and also to just discover the nonlinear dynamics of my system. There are some really big challenges that sit there all over biology, especially, but also in many of the systems we look at nowadays, which are things like multi-scale phenomena, intermittent dynamics, transients. These are things that we often have a very hard time characterizing in these highly complex systems or doing predictions with it. Okay, so let's get into the actual algorithm I want to present to you. And it's going to be centered around here. You give me a nonlinear dynamical system, and X here can be a very high dimensional, can be low dimensional. It's some measurements, some state space I'm measuring. Now the way I grew up in my educational system, you give me N, or I derive N. I give you the system. I do simulations of it, and maybe I have some data available, and I compare it to that data G. Okay? So I would say this is our normal architecture. In fact, I have all kinds of books with different N's. I have one book called Quantum Mechanics, has a certain N. Another one on Maxwell's equations and electrodynamics has a different N. Classical mechanics, different N. Right? We've written these down. And we study them. And now here's the thing. I have a bunch of data. I don't know what N is. I would like to get N back. That's what I'd really like to go after here. So what we want to talk about, think about doing, this is work with Steve Brunton and Josh Proctor. Steve is in mechanical engineering at University of Washington, was former postdoc faculty there now. Josh is at the Institute of Disease Modeling. We want to think about that problem. How can I get N from measurements? And let me just be clear. All this is, it goes back to that first slide. It's AX equal to B, where all I'm going to do is promote sparsity in the solution. Okay? So whatever you take away from here, just remember, I'm not fancy. I'm AX equal to B. Okay? Now, here's what I'm going to do. dx dt equals some stuff. I don't know what that right-hand side was. But what I'm going to posit is that I'm going to say, well, it could be a lot of different things. So I'm going to make up a big matrix, theta, which is a library of all kinds of potential right-hand sides. Polynomials, sine, cosine, whatever, it's up to your imagination. We'll start off polynomials, because we're going to do a lot of the canonical models out of physics, and then we'll go from there. So for instance, this xp2 is all possible quadratics of my state space variable, and here's maybe what this matrix looks like. It could be x1 squared, or x1, x2, or x2 squared. Put them all in. And what the columns are, so that's the columns, and the rows are the different snapshots of time. Now, you have the state space measurement at time 1, at time 2, at time 3, so you can build this entire matrix. Okay? So what we're going to do with that is create an AX equal to B model, which is x dot equals some right-hand side. Now, I've measured the system x, so that means I could also take its derivative to get x dot. So that's my vector B.
Are you simulating to get the answer, or you're taking an experiment?
This would be from an experiment, but here what I've done is I've created my own data.
In an experiment, you have a sensor function. You don't know what the it is, right? You have a sensor function and vector system.
That's right.
Therefore, you only know I have twice, but you don't know what it's measuring.
We'll talk about the hidden variables in a minute. So let me get back to that. There's issues around latent variables. Here, let's say I can measure the system, and I'll get to some examples here that at least get around that. And the system I'm going to go after first is just your Lorentz equations. So here it is. There it is. Okay, I know what it is. And I'm going to do is just run it, simulate it, create a set of data, time series data. And then what I'm going to do now is blindfold myself. I didn't know what created the data. I just have the time series. Well, I have x and y and z in time. I can compute their derivatives. Here is my matrix of potential terms that I made up. And I'm just going to do up to fifth order polynomials. So this is the matrix A, x equal to b. And what I want to do is solve that. But here's the thing I know. What I know is, or what I'm assuming is, that only a small number of columns of that matrix theta matter. I'm going to go for this idea of parsimony. So I want to select the right columns. So I'm just going to solve ax equal to b and promote sparsity. And when I do that, what I end up with is the answer there, and those dots represent the non-zero components that come out from just doing a simple regression on ax equal to b. And what are those terms? Well, they're over here, and they're exactly the Lorentz system. So I measure it and I pull it back. Yeah.
So those are perfect data, the data that you generate without noise.
This is with noise now. So let's get to the noise. A lot of you will skip forward on what you need. What else can you do with it? I'll get to some of them. You can handle it with noise. Here you go. But one important thing, if you've got noisy data, do not do finite differences to compute a time derivative. You must do something a little more sophisticated. We use a total variational derivative for doing the differentiation, okay? Because finite differences is highly unstable. So you can handle some noise. Again, you reproduce the Lorentz equations. Your parameters are only off by a few percent, but you get it back exactly. You can also do more complicated examples, such as this here, which is flow around the cylinder. What I'm going to do is take snapshots of that system. And this is a very high-dimensional system. However, if you take snapshots of that system and you simply do something like an SVD, what you find is that there's 3 dominant modes. And when you do the SVD, there's 3 matrices that come out, U, sigma, V. The V matrix tells you about the time dynamics, the U tells you about the mode. So you can just go look at the V matrix. There's 3 columns that matter. Do your data fitting on those 3 columns. And what do you find? You find, in fact, the dynamics reduces down to this system here, which is, in fact, the normal form for the Hopf bifurcation that occurs in the flow behind the cylinder. So I directly build a reduced order model, consistent, in fact. There's a long history of how that equation came about, actually. So it was first proposed sort of in 71 by Rule and Hawkins that it's like, there's this Hopf thing that happens. That's a possible route to turbulence. And it turns out people were like a little confused about this because Navier-Stokes is quadratic, the Hopf is cubic. How does this happen? Finally closed out in 2003. This is a 32-year gap. Nowak said, hey, actually, the reason this happens is because, in fact, there's this slow-fast interaction producing an effective cubic. We get it immediately from this regression. You can modify this to handle spatial temporal systems. And this is my student Stan Rudy, who, by the way, I have to mention for all of those of you who are at WashU, this is a proud alum. Here we go. So he graduated a number of years ago from here, and he's my PhD student, and he did this for PDEs. And the nice thing that I like to point out about this is not only here we're doing something different, flow around the cylinder again, but I'm going to directly derive the Navier-Stokes equation just from sampling flow behind the cylinder. And not only that, because the low-rank structure dominates, I can massively subsample my data. I don't have to sample all the state space. I can massively subsample, and this gets to some of the questions around if you have low-rank structure exhibited in these systems, you can massively subsample and pull it out. We kind of did all the canonical models of math physics. There they are. Who cares? You can look at the paper. Oh, by the way, all this code's available. You go to my website. There's thing open source code. There's a Python notebook. We'll walk you through all of this. There's MATLAB code for the original part. All of it's there. All the examples. Okay, so now that gets us to this. Fill in the blank. I'll give you a second. Okay, the correct answer is hard. Or you can modify it to extremely hard, massively hard. Difficult's another version of hard, but that's the correct answer to this, just in case you ever see it on a test. So now we get to systems, right, where we don't have clean derivations or clean models necessarily, or even fundamental laws to go down to that we can really pull out and say this is truth, because it's so complex. Yet, the hope is, I think for myself, was around this kind of paper that I read quite a while back. It was a 2008 paper out of Gilles Laurent's group, which was they took recordings off the antenna lobe of a locust, right? And here's what a bunch of spike trains stimulate. They gave it some odor. They stimulate this thing. That's the gray region. They look at the spike train encoding and looks like a mess. However, if you project into PCA space and you look at the top 3 modes, it's a very simple dynamics. It's over at FP, which is the fixed point, and when you give it a puff of odor, what ends up happening is you start here, you come around to here, now you're up here, turn it off, you come back to here. So this system, which has hundreds of thousands of neurons, seems everything's collapsed into 3 dimensions. So this again goes to the observable space. These are sort of the right observables. Some global modes on this network of an olfactory bulb versus individual neurons. And so this is the hope. It's like, well, I should start building models off of this. And in fact, initially, this is exactly what we did. We started thinking about doing data-driven projections into these low-dimensional subspaces. I should build my model. The data clearly tells me I live in a 3-dimensional subspace if I have the right basis functions. And I can get those directly from the data. And then you can start building models off of this. And this was work with my postdoc, Ellie Schlieserman, and Jeff Riffle, who actually had the biological setup to do this. And we got a pretty good comparison between theory and experiment. Actually, yeah, so these are theoretical results of making decisions about 2 odors, whether it was odor A or odor B. And so you could start looking at the experimental and theoretical data, and it didn't do so poorly. We projected this actually onto a known model, which was integrated fire type model, but we wanted to do something fancier now, which is start to think about doing just the data-driven model projection. Now, I know this is way beneath many of you, the worm. I know there's all kinds of snobbery about the worm is not sophisticated enough, but here's what I love about the worm. It's 302 neurons. Its connectome is stereotyped, so every worm is the same. And here's the most remarkable thing, I think, especially when you're thinking about trying to develop control, is it's got 4 things that it will behaviorally do. It will move forward. It will move backwards. It will wiggle its head. It will do an omega turn. So there's no complicated output. This is just like a worm that does simple things. And this is about the level of sophistication I personally can handle. Okay? And I think if we could solve the worm problem, we might be able to upgrade the humans. I think there's a bunch of things in between, right? Like mice and rats. Apparently there's a difference between those. And so one of the things we started looking at and trying to get a feel for the worm and how to handle it is, when you think about control, a lot of times you want to perturb the system and see what happens. And we started doing this from the point of view of thinking about concussions or traumatic brain injuries and neurodegenerative diseases, which often generate focal oxygenal swellings. This is a hallmark feature of Alzheimer's, as well as many other neurodegenerative diseases, is that you see this there. And then we started thinking, well, let's take the statistics that they see in these experiments and let's place them on this 302 neuron network and ask what kind of behavioral deficits you get so we can try to understand the functionality of that worm and why its connectome is made the way it is. Okay? So we can kind of do these things. We can start looking at when the worm is in forward motion. The white circle there in the middle is supposed to be the little limit attractor. These are 2 modes, the eigenworm modes, while it's forward motion. And as you start to perturb this system, you start seeing these colored things as basically as the energy level goes up, how it gets deformed in space until it shrinks to a dot where it can't move anymore. And so this is starting to frame for us the ability to construct potentially a control paradigm. And let me see here. Okay, so yeah, this is the only thing that won't come up since my computer wasn't coming on. What this movie was going to be is a swimming worm, which is very beautiful swimming worm. It's all, 4 things it does. One of them is swimming. Not swimming, it was just crawling. I shouldn't say swimming, it was crawling. And then the second thing it did is much like the videos shown here. So Scott had some, Jeff had some. I don't know if Garrett, you had any, but basically how you see behavioral deficits in people, right? So you see the degeneration that happens and you're trying to compensate for it. In the worm, you can see the same thing. When you perturb it inside, what you see the worm do is starting to look what's effectively like a stutter in their crawling shape, right? And so this is starting to help inform for you how you can bring these data-driven tools onto here and start even just understanding this very simple recovery mechanisms for four dynamical things it wants to do on a very simple model. We have a biomechanics model, a connectomic model, and it also starts to get towards, Garrett, what you talked about with behavioral states. How many behavioral states are there? Here, at least, I can list them. So instead of the infinity of what we seem to have is maybe a continuum or infinity, it really seems to have a very distinct set of infinite number of things out of it. Okay, so I'll finish here. So thinking a lot about a system, I want to sparsely actuate, sparsely record from that system. I want to start learning the features of the system I want to do, build models out of it. I want to also do some uncertainty quantification in this model, and then design adaptive and robust controllers, even if the system state changes. And this kind of generic framework that I presented to you is starting to bring the pieces together. Now you notice I haven't actually done it, but I have a lot of the key pieces, and what we're headed towards is actually putting these things together in some kind of... So what I've done is really some of these boxes, and eventually I'm going to go to this. What's that?
What's the model for the world?
We built a model, so we basically took the full connectome, the approximated experimental values that they have, and also the neuron.
What's the dimension of the system?
302 neurons. We just look at the time series of 302 neurons, and what you find is that, in forward motion, for instance, there's two modes that dominate. So you see that you're starting to write things in macro variables. Like, what's the dynamic of these macro variables? And there's the connectome is clearly built for the function. That's what we're seeing. One of the assumptions made right out from a lot of neuro conferences is like everything's randomly connected. I don't believe anything's randomly connected. The worm clearly shows you that. No, it's completely engineered for the function. And so when you start damaging, you can start asking the questions and assessing that, but also building the right models for the function. So that's kind of where we're going with this. So I'll stop there. Sorry. Okay, thanks.
I guess due to the time constraint, we can take one question.
Well, I just want to pick up on that question. You've got your connectome, and you've got 302 neurons. And then, is there a particular differential equation model for each?
Yeah. So I didn't put it here because I have a whole. That's a whole.
This is the effect.
Yeah. There's a dynamical system for every single, plus the synaptic connections also have dynamics themselves. So I can actually, I can give you those details if you'd like. But yeah, so it's a full dynamical model, which also then we can. One of the key things missing in a lot of these dynamical models is what we find in the worm is proprioceptive feedback from mechanical forces now have to play a key role in sustaining and driving dynamics. So you need all the integration of motor sensory together to make it actually work.
Okay, so let's take our speaker in.